So the first thing I want to talk about is a very simple what the textbook calls value function based methods. Okay. What the textbook calls value function based methods. These are approaches where I don't know the Q star, right, but I am going to try and form a estimate of the Q stars. So how can I do that? So what is Q star? The expected payoff, right? So I play each action, I choose each action say 10 times, I can take the average of that gives me an estimate for Q star, right. So we will denote the estimates by Qt. So whenever we attach a estimate to an action, we will be using the notation Q, okay, just so that you know, so we use Q's here, and whenever we attach a estimate of the payoffs to a state, we will denote it by V. V stands for value function, okay, that is easy to remember, do not ask me what Q stands for. So one of the problems with RL is that because there are so many different influences that came in, right, so you have at least 3 different sets of notations that people use in the literature. Okay. So you would have to swap back and forth if you are reading papers in reinforcement learning, right. So somebody will say that the value function is denoted by J, right, and Q denotes the cost function, right. So if they had used disjoint set of symbols, at least it's easy for us, right, but they'll use the same symbol that one body of literature will call the value function, another body will call that the payoff function, right, which essentially corresponds to the reward that you are getting at every time, right. So that will be denoted by Q. So there all kinds of confusions are there. So, yeah, so this is one set of notations that I am choosing, essentially because it's the one that is adopted in the Sutton and Bartow book. In fact, people who are reading edition 1, right, there has been an overhaul of notation in edition 2, right. So to the extent possible, I will try to follow the edition 2 notation, but edition 1 is ingrained in me, right. So I mean, I have been using edition 1 notation for God knows 15 years or something, right. So suddenly they decided to change the notation in edition 2. So by force of habit, I might slip into edition 1 notation occasionally. So it's in your well-being to read ahead so that you can correct me whenever I do that, right. Just don't wait for me to teach and then go and, or well, don't wait for the quizzes and then read the book, right, but read ahead and come to class, okay. This will certainly help you significantly in following the material better, right. So I am deliberately going slow today, warming you up, okay. But then there is lot of material that we cover. In fact, usually I cover the material in the book in about 1.5 months, right, and the rest of the time I will be doing material outside the book, right, 1.5 months, 2 months, something like that. Okay. So the book is big, right. So at some point I will switch modes and start going fast. So reading ahead helps. Okay. So we are going to have Qt. So essentially what you can do is you can just take whenever I took action A, right, the reward I got at that time, right, I can just keep adding those up and divide by the number of times I took action A, that will give me my Qt, right. So how will we write this? Let us introduce some notation. So that is a notation that I will use whenever I want an indicator function, right. So normally what is the notation that people use for indicator functions? Huh? I or delta, right? So people typically use delta or I. So I'll use 1 because we use I and delta for other things later on. Okay. So this essentially means that it is 1 whenever AT is A, otherwise it's 0 times so what should I divide this by? Okay, so this gives me the average, right? Great. So once I have this, now I have made an estimate for my Q stars, right? Once I have an estimate for my Q stars, so how will I select an action? Apologies. Okay, so I use t on the left hand side, so I can't use t as the running variable as well. Okay, so now I have come to time t, I have these estimates for my Q stars. So how can I use that for selecting actions? Select the maximum, right? So I could be what we call greedy. Right, so greedy would be I am going to select right. So I will take that action that gives me the max. Okay, so argmax is the action that gives me the max. Right, so I will take that action that gives me the max and use that as the action to perform at that time, right? Is that a good choice? Or alternatively, what does this choice correspond to? Exploitation. This choice corresponds to exploitation. But I can't just exploit, right? I have to explore as well, right? So I can't come up with an algorithm that only exploits, right? So what do you think will happen? Let us say that I pulled an arm, right, the first time. Well, I select an action and then I get a reward of 1, let us say, right. So what will happen to my Qs? It will be 1. What about my other Qs? Well, it depends on what you initialize them with. So if you initialize them with 0, they will stay at 0. Right. I could have initialized them with 100, right, or could I initialize them with minus 100, I don't know, right? Whatever it is, I initialize them with, they will stay there, but this one will become 1. Right. Now, if I am doing greedy, what will happen? I will do this again. Let's assume that I get a 1 again, right, and then keep getting 1 every time I pull this. So what will happen is I will never ever sample any of the other arms, right. It could very well be that arm 3 has a reward of 50, right, just because I happen to pull arm 1 the first time, right. I will never ever go and pull arm 3 even though it has a much higher reward, right. So we don't want to be exploitative completely, so we need to have some kind of a exploration policy. So the simple exploration policy, okay, so I am going to confuse you a little bit, is called epsilon-greedy. Nothing to do with this epsilon, okay. So this epsilon is completely different, okay. It talks about a solution concept, and just because I have something epsilon-greedy doesn't mean I am going to give you some epsilon pack guarantee, okay. This is a completely different epsilon. In fact, it was named epsilon-greedy before people even started thinking about bringing all these pack optimality questions into RL, okay. So what does epsilon-greedy mean? Any guesses?
Choosing within epsilon of the greedy solution.
Sorry?
Maybe choosing within epsilon of the greedy solution.
Within epsilon of the greedy solution. Okay, good choice. But I said that it has nothing to do with this epsilon. It's got nothing to do with this epsilon. What I do is, with probability 1 minus epsilon, I will be greedy. Okay, with probability epsilon, I will just explore. Okay, so epsilon greedy means with 1 minus epsilon, I will choose with probability 1 minus epsilon. With probability epsilon, I will choose uniformly from the set of actions A. Okay. So one thing which you should note here is that if I choose uniformly from A, I still have a probability of hitting that argmax A. Right. So in fact, the probability of me taking this action is 1 minus epsilon plus epsilon by n. Right. The probability of me exploring is actually n minus 1 epsilon by n. Okay. So this is something which is just a small thing, nitpicking thing, but just remember that. So the probability of exploration is not epsilon. Okay. Because I'm picking uniformly randomly. You could choose to say that I pick uniformly from A minus this argmax action. Right? It doesn't make a difference. But I'm just pointing out that there is a small difference. Just remember that. Okay. So epsilon greedy by far is one of the most popular exploration. It's by far the most popular exploration strategy that people adopt. Okay. By far the most popular exploration strategy. There is another one which ironically I couldn't find in edition 2 of the book, which is also rather popular. It's called Softmax, or maybe I flipped through edition 2 too quickly to notice it. So the Softmax exploration policy does something slightly cleverer. Okay. So if you think about the epsilon greedy, what is it that you would notice is that I have the best action, best according to my current estimates, right? So whenever I say greedy or best, it is according to my current estimate. It's not Q stars. Okay. It's according to capital Q. Whenever I say greedy, it's according to capital Q. Okay. So the greedy action gets the bulk of the probability, right? And every other action has a equal probability of being picked in exploration. Correct? But then if some actions are clearly bad, right? If I figure out some actions are clearly bad, so I don't want to be picking them during exploration, because I know that they are bad. I really don't want to be picking them during exploration, or at least I want to reduce the probability of picking them during exploration. Right? And if two actions look equally likely to be good, right? Maybe a 0.0001 difference, right? Some small delta difference between the two actions. In epsilon greedy, what will happen? The one that is that 0.0001 higher will get the highest probability. Okay, and the other one will have the same probability as all the other arms of being picked, right? But then in reality, I just want to be able to compare these two things more closely and figure out which one is better, right? Because the difference is so small, I really want to compare them and figure out which one is better, right? So what people did was they came up with this Softmax idea, right? Where instead of giving all the probability to one action, right, I make the probability of picking the actions proportional to the estimate, current estimate. So whatever is the current Q, I will make the probability proportional to the Q, right. So ideally it should be something like so this should be the probability with which at the Tth step I will pick action A, right. That should be the probability, right. What is the problem with that?
Numerically they might be of different orders.
of
Like one of them might be minus one, another might be plus one.
different orders,
Not orders.
yeah, different signs.
Different signs.
Right, so I mean, so the things could be also, so it could be negative numbers. In fact, I could even end up with a negative probability. Right, if my qt of a was minus 1, right, then I will end up with a minus something as the probability of picking that action. Doesn't make sense, right? So to encompass all kinds of options, what do we do? Exponentiate. Right. So why is this called softmax? Because it is not greedy, it does not return to you the one that has the highest q value all the time. But if there is a big difference, it will return that value to you most often. Let's suppose there are 4 actions, right? And action 1 has a value of say 19, action 2 has a value of 1.2, action 3 has a value of 0.7, action 4 has a value of minus 0.3, right? So now this will return to you, most often it will return action 1 to you, right? So because that has a significantly higher value, okay, that's why it's called softmax, right? Sometimes what people do is they throw in another parameter called the temperature parameter sometimes, so beta, right? So now think about it, if beta is very, very high, so what will happen to your softmax function?
Relatively,
Huh?
relatively even a larger value will.
Everything will get squished down, right? So if beta is very, very high, so essentially you will be behaving at random, uniformly random, right? Because all the, regardless of what the q values are, right? If the beta is very, very, let's say beta is 1 million, right? And I say it's 17 and 1.8, no, doesn't make any difference, right? All of them will look close to 0, right? So essentially I will be picking all actions uniformly randomly, right? So this way it's called temperature. So if you are very, very hot, right? So things will move around at random, right? And then people typically cool it down. So they make beta smaller and smaller and smaller, so that from a very high temperature where you are essentially behaving at random regardless of what the q values are, as you keep cooling it down, it becomes more and more peaked. So if beta becomes closer and closer to 0, what happens?
It gives all probability
Max
to
value.
one.
It becomes max, right? As beta goes to 0, this function goes to max, right? So it becomes greedy. So it gives you an additional parameter for tuning. I mean, if you don't trust me, you can work it out, right? You guys are smart enough to work it out, right? So this gives you an additional parameter for tuning how sharp your probability needs to fall, right? So this is called softmax. And so if you think about epsilon greedy, then writing it in this notation, so this will be right. So probability AT equal to A star will be 1 minus epsilon plus epsilon by n, where A star is the greedy action according to the current estimate, right. The probability AT is not equal to A star, or probability AT is equal to A which is not equal to A star will be epsilon by n, okay. And likewise here you have this probabilities here, okay. So these are the two rather popular ways of selecting actions. In fact, epsilon greedy and softmax are also used in the full reinforcement learning problem, right. It's also used in the full reinforcement learning problem for selecting implementing the exploration policy, right. I mean, you can convince yourself that epsilon greedy, very simply you can convince yourself that epsilon greedy, right, will give you asymptotic correctness provided something, but can you convince yourself that it will give you asymptotic correctness? Right? I mean, you are always going to be taking all the actions, right? So eventually you will converge to the true expectations, right? You will eventually converge to Q star because you are taking all the actions all the time, right? So, but what is the problem? If I keep my epsilon fixed at some value, let us say I keep epsilon fixed at 0.1, right? 90% of the times I am behaving optimally, 10% of the times I choose at random, right? So what will happen? I will know the right Q stars after a long time, but I will still be behaving randomly 10% of the times, right? What asymptotic correctness says is, eventually I should be only giving you the behaving according to the right arm, right? So I should be only doing the right choice eventually. To achieve that, what should you do? You have to cool epsilon, right? So epsilon has to keep decreasing, but then you shouldn't decrease it too fast. If you decrease it too fast, then you don't have the guarantee that you will get the correct Q stars, right? So there are ways in which you can balance this, right? And so in fact people show that if epsilon falls as 1 by t, right, that's usually a sufficient rate, but unfortunately that will actually slow down your convergence tremendously, because it becomes truly an asymptotic convergence. I mean, you have to run it till infinity for you to get convergence. So in practice what you can do is you can cool it in steps, right? Set a high epsilon, right, run it for a while, okay, and then drop it a little bit, and then run it for a while, and then drop it a little bit, then run it for a while, and so on and so forth, right? So figuring out how long the while should be is a tricky question. Depends on a variety of factors, but you can do some kind of empirical estimates for the time being, right? Good. So do we move on from here? Okay. So before I go on to regret optimality, there is one small thing which I want to talk about, right? So here I gave you a way of estimating the QTs, right? So what do you notice about that? I run experiments till time t, right? And then when I want to know what QT is, I look back and see how many times I have taken action A, and then I take the average, right? So that essentially means that at time step t, I need to know what were all the actions I picked earlier and what were all the rewards I got for those actions, right? So I need to remember this whole history, right? So is there a more efficient way of doing it? Huh? Sorry?
Work with probability of picking the action.
Don't get it.
1 minus alpha times of history plus alpha times of number.
Yeah. So I can essentially do this in a kind of doing the run. I can do this running sum, right? So how do I do that? Right. So I want QT of A, right? So it is some numbers, right? So it will be essentially QT minus 1 of A, right? So let me introduce a little bit of a notation. It will make my life a little easier, okay? So the number of times I have taken action A, I will denote by NA, okay? Right, people will agree with them? Yes? Okay, great. So assuming that I actually took action A at this time, right? So what will happen? Okay, you want me to erase and rewrite? Both the numerator and the denominator, or only the denominator? Numerator is fine? Okay. I am assuming this is fine. So now I can do this in a incremental fashion. Right, so this is Na by Na plus 1, RT by Na plus 1, I can just keep adding this, right? Right, so I don't need to remember all the rewards, all I need to know is how many times I have taken action A so far and what is the previous estimate of Qt, right? If At was not equal to A, what happens? This will vanish, the Na will get cancelled, it's just the same thing, okay? So no change. Right, is there a different way we can write this? Go on.
Qt minus 1 of A.
Qt of A, okay.
1 minus of 1 by Na plus 1 plus RT.
Is it fine? Yeah, people agree with that? Right, this is Na by Na plus 1. So I can write it as 1 minus 1 by Na plus 1, right? Great. Now I can rearrange these quantities and get a better looking expression. Right? Looks good. So this is a form of a general class of equations known as stochastic averaging equations. Right? And there's really no stochasticity that you need to worry about here, but this is called stochastic averaging equations. So one way to think about it is, I have an old estimate, right? And to that old estimate, I add a error term. So what is the error term? This is my target, right? I should have predicted the reward is RT, right? So this is my target and that is my actual output, right? Qt minus 1 is what I said will be the payoff. RT was what the actual payoff that occurred, right? So RT minus Qt minus 1A is some kind of a error term, right? And this is some kind of a step size, 1 by Na plus 1 is some kind of a step size. So what I am doing is I am taking my old estimate and adding some alpha times an error. Okay. So many iterative algorithms that we have looked at, even if you had taken ML, that some of the algorithms we looked at in ML, right, and many iterative algorithms that we will look at later in the course will all have this form, old estimate times, plus some alpha times an error term, right. So what is the thing that you should note here? Why is it called stochastic averaging rule? What I am really trying to find out, what my real target is what is my real target? The expected value of RT. My real target is not RT, right. My real target is the expected value of RT, right. So my actual error should have been expected value of RT minus QT minus 1, right. That would have been my actual error. But since I do not know the expected value of RT, so what I am using here is some kind of a measurement of that expected value, right, and the unbiased measurement is a sample drawn from the distribution according to which you are taking the expectation, right. When I say expected value of RT, right, so RT is a sample, right, I am going to take the average of all these samples and it is going to give me the expected value. Since I do not know the true expectations, I can operate with these samples, right. So I am going to form an estimate of the target or estimate of the error, right, by using a sample as opposed to using the true expectation. That is why we call these as stochastic averaging rules. And so this is a very standard form that we will keep seeing again and again in all the algorithms that we will look at, right. So current estimate plus target minus current estimate, right. So this is the thing, right. And this particular choice for my alpha here, 1 by Na plus 1 gives me the exact average. This is exactly, I did no approximations anywhere. This gives me exactly the same estimate as I would have obtained by storing all the values and taking the average at every time, okay, right. Yeah, so we will stop here today, or maybe I can just do one more thing and then we can move on to the other things in the next class. So far we have assumed that your coins are not changed, right. So we are assuming that the distributions from which the rewards are sampled or the payoffs are sampled is stationary, okay. Constant has a different meaning. It's stationary. Stationary means it does not change with time, okay. So if it is, so when I say something does not change with time, what does it mean? It means the coin does not change with time. It does not mean it always comes up heads, okay. When I say something is stationary, okay, it does not mean that the outcome is always the same, okay. It means that the distribution from which I am sampling the outcomes is always the same, okay. But sometimes you might have non-stationary problems, right. So it's essentially you keep tossing the coin one side starts wearing off a little bit, right. So after a while it might start falling tails more often than heads, or what will happen if the head wears off? Will it start falling heads more often or tails more often? Start falling heads more often, right, because there will be more metal on the head side, so it will be heavier, so it will tend to come at the bottom more often. So if head starts wearing off, okay, it will tend to come relatively more frequently on the top than it used to earlier. Anyway, fine. So things will start changing over time, right. And so what do you do in such cases? So you need a way, there are technical ways of handling it, I am just giving you a practical way of handling it. You need a way to be able to track the changes over time, right. So if I am going to use this kind of an update, so what will be the problem? After I have pulled an arm say 1000 times, right, this number will become very small, right, it will be 1 by 1000 plus 1, like it will be 1 by 1001, right. So the impact of the new samples I am drawing will become smaller and smaller and smaller, right. So suppose I pulled an arm 1000 times, okay, 1001st time I pull the arm, right, the impact will be very, very small, right. If you think about it, I am averaging like 1000 numbers, any individual number is going to have a very small impact on the average, right. But this is all fine if I am sampling from a stationary distribution, because I already drawn 1000 samples, what is the 1001st sample going to tell me? Right? But if I am drawing from a changing distribution, so the more recent samples are more important to me than the older samples. Right? If things are changing, if my coin is varying out over time, then the more recent samples are more important to me than the older samples. Right? So what do I do in such cases is where alpha is less than 1. So you can do a little bit of expanding out on this, and you can convince yourself that as time passes by, the older rewards that I get will get exponentially lesser weight. Right? The first time I do this, right, the new reward will get a weight of alpha. Right? But second time I get another reward, what will happen? I will get a weight of alpha squared going in there for the older reward. Right? The new reward will still get an alpha, the older reward will get an alpha squared. Right? So like that, so I will be paying more and more attention to the newer rewards, right, and the older rewards will keep getting decayed. Right? And all I did was a very simple change. Instead of having 1 by n, I made it a constant alpha. So making it a constant alpha actually allows me to pay more attention to recent rewards and less attention to the older rewards. Right? And depending on how quickly your rewards are changing, you can tune the value of alpha. Right? So problem with keeping alpha fixed is what?
Might start oscillating about the point if it doesn't play much.
If it is stationary, right, you will not converge. If it is stationary, you will still not converge because you are still paying attention to the more recent rewards, right, and you will keep oscillating around the true reward. Right? So whenever you get a 1, you will go up, whenever you get a 0, you will come down, up, down, you will keep going like that, right, because you are paying more attention to the recent rewards. Right? But the advantage of keeping alpha constant is that if it happens to be non-stationary, right, you will track it to some extent. Okay? There are other more robust ways of tracking non-stationary problems, but this is a very simple trick that you can use. Right? And more often than not, we will actually end up using a constant alpha in many of the algorithms that we will look at. And but whenever we talk about theoretical convergence, we will always talk about alpha decaying. Right? Whenever we look at practical implementations of these algorithms, we will always have a constant alpha. Right? So the problem with decaying alpha as 1 by n is again the same thing which I told you with decaying epsilon. Right? The changes will become small very fast. Right? So that's always a trade-off that you have to pay. Okay, so good.